Derivatives of Laplace transform or multiplication of powers of t. If the function ft is a sectionally continuous function and is of exponential order, then the statement of the theorem of derivatives of Laplace transform is the Laplace transform of t raised to power n ft will be equal to minus 1 whole raised to the power n d raised to power n upon ds raised to the power n fs, where n is equal to 1, 2, 3 and so on. So the theorem of derivatives of Laplace transform or multiplication by powers of t is if any function ft this function ft is a sectionally continuous function, that is, there is piecewise or sectionally continuity in this function. As you know, sectionally continuous function is that function which remains continuous for all intervals of time t. That is, if a closed interval AB, suppose time starts from A to B, between this interval, suppose there are so many sections. If the given function remains continuous in all these sections, then that function will be called piecewise or sectionally continuous function. Second thing is, this function is the function of exponential order. It means when limit t tends to infinite e raised to power minus at ft is equal to finite. So in the theorem of derivatives of Laplace transform or multiplication of power by t, we are using one function, and the quality of this function, property of this function is this function ft is a sectionally continuous function as well as it is a function of exponential order. So it has two qualities. Number one, it remains continuous for all interval of time t, and for this function the value of limit t tends to infinite e raised to power minus at ft is finite. This function ft satisfies these two conditions. We are choosing such type of function. Then theorem of derivatives of Laplace transform or multiplication by power of t is this function, which is sectionally continuous function as well as it is function of exponential order, the value of Laplace transform of t raised to power n ft is equal to minus 1 raised to the power n d upon ds raised to the power n fs. Or we can say that Laplace transform of t raised to power n ft is equal to minus 1 raised to the power n fn s. So we can prove it. The theorem of derivatives of Laplace transform or the multiplication by powers of t is, we will choose one special type of function which is sectionally continuous function as well as it is function of exponential order. For such type of function, Laplace transform of t raised to power n ft is equal to minus 1 whole raised to the power n d upon ds whole raised to the power n fs. Or we can say Laplace transform of t raised to power n ft is equal to minus 1 whole raised to the power n fn s. Here n is equal to 1, 2, 3 and so on. Now we can prove this theorem in the two cases. Case number 1, when n is equal to 1. In this case, we can prove the theorem of derivatives of Laplace transform. Similarly, second case will be when n is equal to r. In these two cases, we can prove the theorem of derivatives of Laplace transform. So let us take first case. Let us calculate d fs upon ds, which can be written as f dash s. By using the fundamental formula to calculate the Laplace transform of any function, it will be equal to d upon ds integration 0 to infinite e raised to power minus st ft and dt. Now if we solve it, then this can be written as 0 to infinite del upon del s e raised to power minus st, then ft, then dt. Differential del upon del s of e raised to power minus st will be, it is 0 to infinite minus t e raised to power minus st ft dt. Or it can be written as minus dfs upon ds is equal to 0 to infinite e raised to power minus st t ft and dt. This can be rewritten as minus 1 d Fs upon ds is equal to L T Ft, because this is Laplace transform of Ft. This can be written as minus 1 f dash s equals to Laplace transform of Ft. Now, what is our aim? Our aim is to prove the theorem of derivatives of Laplace transform. Here in this case, this proves that the theorem is true for n is equal to 1. In the second case, we will take this theorem is also true when n is equal to r. So we have covered the proof of first case, that is n is equal to 1, and in the next lecture we will prove the same theorem for the next case when n is equal to r. Thank you.